Mr. Sadler.
And today we wrap up our discussion on the physics behind car accidents, and we're going to talk about a new topic today. We're going to talk about the topic of impulse. And so on our whiteboard, we've been putting the terms up and linking them together. And as I look at the whiteboard as I'm sitting here, I see that impulse is connected to a lot of things. It's connected to Newton's second law. It's connected to the third law. It's connected to momentum and conservation of momentum. So impulse is kind of like work, where we said work could be equal to the change in the kinetic energy or the energy of the system. So by doing work on an object, you give the system energy. And you did that work by applying a force over some distance. And we analyzed this with respect to the airbag. Impulse is just like work, except instead of dealing with energy, impulse deals with momentum. So impulse, okay,
It's really like a change in momentum, right?
is just the change in momentum. Now, there is no fancy symbol for it. We just call it delta P. Okay? And so to determine the change in momentum, you would multiply a force times a stopping time. And we could have just as easily used, so we used work to talk about airbags, we could have just as easily used impulse to talk about airbags. But today we're going to use impulse to talk about crush zones or crumple zones.
It's funny, when I was thinking about this, I was thinking that really a crush zone in a car is exactly the same as an airbag.
Right.
It makes the accident last longer, so there's less force.
Right. So remember at the very end of podcast 1, we said longer accidents equal safer accidents. And I had a few students ask me about this. This doesn't mean that I want that after the accident is done that you should stay in the car.
Right.
This means that the physical event of the crash needs to last as long as possible. Crush zones do that, airbags do that, seatbelts do those things. If you take away all of those safety features, then the event is short, and the force on you goes up. And when I can say short, I can say short stopping distance and short stopping time.
Right.
Right. So how does this work out? Well, there's a lot of ways to do this. Your book does a nice job of walking you through this on pages 324 through about 329. There's a lot that goes into this. And what we're going to discover is that if the change in momentum is equal to the force times the time, we can make both sides of these equal signs work together. And because this is mass times acceleration times the change in time, and this would be mass times the change in velocity. And this, by the way, we show this on a Plus podcast inadvertently. What ends up happening is you start to see some things that look really familiar. And you can start to make some stuff disappear through substitution. And it's important that both things on either side of an equal sign are actually equal to each other. And all of a sudden we just went from impulse to momentum.
Mm-hmm.
And we could talk about accelerations and just break out Newton's second law. But there's a lot of stuff that we could do here. All right, but what we're trying to get across is it's all connected. None of these ideas stand alone by themselves. So why would we introduce impulse, which deals with a change in momentum, if we have work, which deals with a change in energy? Would it have been possible to look at airbags with impulse?
Yes.
Yeah, and would it be possible to work at crumple zones with work?
Yes.
Right.
So it's just two ways to find the same
Two
thing.
ways to maybe find the same thing, but there's some information if we focus on the equations. Okay, this is energy, and so we're clearly going to use joules.
Hmm.
So that's one feature. This is momentum, so we're clearly going to use kilogram meters per second. Okay. But as far as measurables go, think back, chapter 1, we did a lot of time making distance time graphs, speed time, acceleration time graphs. Those were things that, since we graphed immediately, that were very easy to measure. Okay?
Right.
Is it easy to measure work
No.
or energy?
No.
Is it easy to measure momentum?
No.
What about force?
Mm,
I think it's easier,
easier.
but it's not easy.
No.
But a time measurement,
Right.
that's
Is easy.
That's easy. And a distance measurement,
Easy.
easy. So this is generally, if I'm going to use the concept of impulse, then I must have time. I must know about the time change. And if I'm going to use work, what am I going to know about?
Distance.
The distance. I'm going to know about d. All right? Because those d and t are easy things to measure. And so as a result, because they're easy to measure, that's how I pick the solution to my problem. So just because on a test or a quiz question you see airbag doesn't mean you need to go to the work solution. There is another way that would be impulse. Just because you see crumple zone doesn't mean that you have to use the impulse solution. You can in fact use work if you have some distance information.
Oh, so we talk about this a lot. Write down what you know and find the easiest formula rather than try to force it into something
Right.
that makes it more difficult.
Yeah, force-fitting solutions very rarely works. In fact, you end up working in circles or getting nonsense answers like infinity. So it's important that you take the time, analyze what you have, use your brain and think about which solution is best. The only other thing I wanted to show is when we talked about work, we said, look, if you give energy to a system or take energy from a system, work had to be done to maintain the conservation of energy. So, in order to maintain the conservation of momentum, if you give momentum or take momentum from a system, then impulse must happen.
Okay.
Okay? So there's some really nice graphs in your book on page 328. And they talk about, they're focusing very specifically on cars with crumple zones versus cars without crumple zones. So, if this is time, and this is force, because remember, our impulse equation is the force times the time.
Mm-hmm.
Okay, so we've got an x and a y axis. Great, everything's working out for us. If this is no crumple zone, what can you tell me about the force?
Large force over a small time.
Okay, so big force over a short time interval, and the area under the curve is the impulse. It's the force times the time. It's a multiplication problem. It could be
Okay.
prettier if it was, if things weren't round. Okay. So that's no crumple zone. What's going to happen with a crumple zone?
Less force over a longer time.
Right. And the area should be
Exactly the same.
exactly the same. So here I have a force that's spread out over a much longer period of time. All right. And what I'm saying here is that the blue area would have to be equal to the red area.
Right.
So this F delta T would have to be equal to this F delta T. Longer accidents mean lower force, mean safer for the passengers.
The momentum's the same of the two.
The change in momentum is
Yeah,
the same.
correct.
The car is still going 30 miles an hour,
Right.
still going to come to
whether
a stop.
stop against a tree or stop against just slowing down with a brake.
Right. It's just a matter of how long that force is distributed for. That's a really important note. All safety devices actually do this. Knee pads, helmets, shoulder pads in football, all of these items, are just taking this force and lengthening the amount of time that's exerted on you, keeping you safer.
Just a simple baseball glove does the same thing.
Baseball glove, great point. So I believe that covers the basics of impulse and how it relates to change in momentum. So signing off, this is Mr. White.
And Mr. Sadler.